Okay, so now welcome to the last section of AP Statistics. And this is actually going to be a throwback all the way to Unit 2 when we were looking at linear regression and using a least squares regression model to make predictions. Now we're going to use an LSRL model to make some inference here, or inference information about the slope. Now there are several parameters in linear regression. The big idea is that there is a real, true linear relationship, and this is coupled with random variation that produces such data. Each sample is unique, however, each sample gives us more insight into the true slope of the relationship of the situation. So think about in physics when you're conducting an experiment, and you're looking at how the forces of gravity interact or how the different forces interact with one another. Although you're all collecting your own data and making independent observations, what ends up happening is that you all are getting a better idea of these lines of best fits that actually model this true natural phenomena of physics, which follows the pattern that we develop in these formulas and such. And so although each of you has your own unique sample, there's a true slope that exists of this relationship, of this phenomena that we're modeling. Now, we use the line y equals alpha plus beta x plus epsilon. So you're going to learn some Greek in this course, where alpha is the y-intercept of the true linear relationship. Note that this is not the same alpha that is our significance level when doing hypothesis testing. This is just the true y-intercept. Beta, not our type 2 error, but the true slope of the linear relationship. And epsilon represents random variation, and this can be due to human error or just the natural error that exists in the universe. Now, we can also write this equation as mu of y equals alpha plus beta x, which indicates that for any particular value of x, the linear relationship produces the mean response for that value of x. Now, our two parameters of interest, the intercept and the slope. Of these, the slope is much more interesting because the slope is all about change, and much of mathematics, particularly calculus, is concerned with this idea of a rate of change, of this constant of proportionality. Now, thinking back to Unit 2, we used the following model for our LSRL, and this was y hat equals a plus bx. Now, we use this model, our sample, to inference information about the population, y equals alpha plus beta x plus epsilon, where we have the following sample statistics measuring the following parameters. Y hat is our predicted response, which estimates y, the actual response. A is our sample intercept, which estimates alpha, the population intercept. B is our sample slope, whereas beta is the population slope. And the standard error of B, or the standard error of the slope, estimates sigma, which is the population standard deviation. Now, back to linear regression, we learned about these concepts, describing a scatter plot, correlation coefficients, least squares regression lines, residuals, the coefficient of determination, the standard deviation of the residuals, and then unusual points. And although we spent a good chunk of time on those concepts, they're going to come back now and help us to develop conditions that we need to check when we decide to do inference for slope. Now, we're only going to learn two procedures for the slope. We're either going to estimate the slope using a confidence interval or find statistically significant evidence about a slope of the true linear relationship, or the true slope of the LSRL for this population regression line. Now, let's go back to Unit 2 first and make sure we review a few concepts here. So I'm going to use the AP Statistics exam FRQ number 5 from the 2005 release year. And it says the Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain route between OKC and Omaha. A random sample of 10 trains on this route has yielded the data in the table below. A scatter plot, a residual plot, and the output from the regression analysis for these data are also included. So here I have the following pieces of information. I have my inputs and outputs for the model. This is what actually happened. Here is a scatter plot, which we know communicates bivariate data. When describing a scatter plot, we use DUFs, which is direction, unusual form, and strength. Here's our residual plot. We don't want any evident pattern in our residual plot. And then here's our computer output, and we know how to interpret each of these values here, with the exception that we're ignoring R squared adjusted. And in this unit, we're going to be learning about what the rest of these values in the computer output relate to. So let's first start off by describing the scatter plot of the data. So I look here back at my scatter plot. Direction looks positive, as I can see the points are rising from left to right. Looks relatively linear. I can see that they're changing at about a constant rate. And I would call that relatively strong because we can see that the points are very clustered clustered together if I were to draw a line through this data. So I'm going to say that there appears to be a positive, strong, linear relationship between fuel consumption and number of rail cars. So that's my description. And if I was asked to interpret this description, I would say that on average, as the number of rail cars increases, fuel consumption also tends to increase. Now the next part here is to determine the correlation coefficient, which is R. Well, back to the computer output, I have R squared, and we know that R and the slope of the regression model both have the same sign because obviously it's tracking the correlation, so it should measure that same rate of change, right? So based on the direction of the slope, this tells me information about my correlation coefficient. So since this is R squared and I want R, I decide to square root it, and then the sign is determined by the sign of the slope. Here we have a positive slope, so I'm going to have the positive square root of 0.967, and this is going to give me positive 0.9833. Now this correlation coefficient tells me two pieces of information. One, it tells me the strength, which is the numerical value. Here, the strength is 0.9833, and we had our three categories of weak, moderate, and strong, and the cutoffs were anything 0.5 or less was considered weak. Anything between 0.5 and 0.8 is considered moderate, and anything 0.8 and above is considered strong. And this is looking at the absolute value of R. Now that's the strength. And then the sign tells me the direction. Positive, which means as x increases, y tends to increase, or negative, which tells me as x increases, y tends to decrease. So the two pieces of information I have about the correlation coefficient are the strength and the direction of this linear relationship between the two variables. Now, in order to define my LSRL, I go here to my computer output. My constant is the intercept, and the slope is special, so it gets a name. So here, when I define the equation, I get y hat equals 10.677 plus 2.15x, where x is the number of rail cars and y is the predicted fuel consumption. I can now use this model to make a prediction, and if I want to predict the fuel consumption of a train with 28 rail cars, I would substitute in 28 for the value of x. So here, that looks like 10.677 plus 2.15 times 28, which gives me a predicted fuel consumption of about 70.877 units per mile. So hopefully this is all a review. If I'm going too fast, watch this in half speed, or go back and watch it again, or process it first and then go back and try it. Maybe try it on your own first, then watch this, whatever your statistically significant heart desires. Now, suppose a train with 35 rail cars produces a residual of negative 4.3. Find the actual fuel consumption of this train. So I know that a residual, this is AP statistics, actual minus predicted. Well, I need to find y here. So I'm going to find the predicted fuel consumption. Using my model, I get a predicted fuel consumption of 85.927. And then I manipulate this equation here to solve for y using inverse operations. So the actual fuel consumption is just the residual plus the predicted fuel consumption. And when I substitute in my values, I get an actual fuel consumption of 81.627 units per mile. Now, notice here that my predicted value was greater than my actual value. This led to an overprediction. And even though it's a negative residual, this happens here because if I manipulate this equation, 0 is greater than y minus y hat, which is why our residual is negative. Now, to interpret the slope of this model, this 2.15, for each additional rail car that is added, we predict an increase in fuel consumption by approximately 2.15 units per mile. So each time I add a rail car, fuel consumption should theoretically increase by about 2.15 units. Now, if I want to find the difference between two trains with separate rail cars, I would use my model to predict both values and then find the difference between the two. Now, you can go straight to plugging and chugging, or you can realize that The slope indicates the rate of change between these two values. So you can either just do the slope times the difference of the values, or if you're like me and you don't believe the tricks, you can just go ahead and use the prediction models and then find the difference. Here, the difference between 23 and 32 is a fuel consumption of 19.35 units per mile. Now, interpreting the Y-intercept for this model is that we would predict a fuel consumption of 10.677 units per mile for a train with 0 rail cars. I don't know why that is. In the context of this question, it's kind of weird that if you're not even moving or you have no rail cars, maybe you're only using 10.677, or maybe it's just like the front part of the train that's moving along, so you're still using gas, but you're just not using as much gas. Now, S in the computer output represents our standard deviation of the residuals. And we know residuals are the difference between actual and predicted values. So here, on average, actual fuel consumption differs from the predicted fuel consumption by about 4.361 units per mile. So there's that on average, the variation between the actual and predicted is 4.361 units per mile. Now, our coefficient of determination, or r squared, not r squared adjusted, just r squared, tells us that 96.7% of the variation in fuel consumption can be explained by its linear relationship with the number of rail cars. This is strong evidence that a linear model is appropriate. Of course, we would need to see the residual plot and the scatter plot, but here, since we do have those pieces of information, we're good to proceed with this. And remember that good models tend to have low S values and high coefficients of determinations. So those are some more interpretations. What is a good indication that a linear model is appropriate? Well, a relatively linear pattern in the scatter plot, which is what we have, and then no evident pattern in the residual plot, because the residuals should just be completely random. And we had both of those pieces of evidence. So for this situation in particular, a linear model is appropriate. So in a scatter, you want a pattern, and in a residual, you want you don't want a pattern, you want it to rebel. So that's the way we remember it in class. Now, would it be appropriate to use this model to predict the fuel consumption of a train with 65 cars? So I'm actually going to go back to where my initial data was here. We're just scrolling on up. Here I look, and most of my data varies between 20 rail cars and 50 rail cars. So 65 is going to be somewhat outside of the domain of the data that I have. So my LSRL model might not be reliable for such a large prediction, since it falls outside of the domain. I don't know if the conditions are the same, or if there's more change or variation. So it would not be appropriate to use this model to predict the fuel consumption of a train with 65 rail cars, since this value falls outside of the typical domain of the model, again between 20 and 50 rail cars. Predicting such a value would lead to extrapolation. Remember, that's just over-predicting, not over-predicting necessarily, but predicting outside of the constraints of our model. And then lastly, an 11th data point is added, and I said suppose, this didn't actually happen, but what if? And the description of this point is a train with 30 rail cars and a fuel consumption of 120 units per mile. What type of unusual point is this? How do you know? Recall we have 3 unusual points. We have outliers, which have the largest residual. We have high leverage points, which tend to be outside of the domain. And we have influential points, which significantly impact the correlation coefficient. And typically, what we just saw in the previous question with out predicting from our model, that generally leads to an influential point, since it still follows the linear trend of the data, but it just might not be as reliable. So this point here would be considered an outlier, since that's a very large prediction given the current trend of the data. So this point falls outside of the general linear trend, in addition to having the largest residual, which is the definition of an outlier. So if we go back to the scatter plot here, this is just saying, okay, here at 30, we have 120. We can see it falls outside of the pattern, and it's got just a very, it's got that large residual going on. So this was just a brief review of all the concepts we learned in linear regression. Note we did not cover transforming nonlinear data, but we're not going to worry about that for now. So that's going to just be our refresher. And in the next few lessons, we're going to talk about inferencing slope for these population LSRLs.